So we're lecture 1, which we've done part of yesterday, just kind of trying to do the skull. We talked on about some of the terms used. So one's kind of designed to introduce the skeletal system, talk about terms used to describe various depressions, elevations on bones. And then if we get to it, we'll start lecture 2, which is where we're going to begin to talk about bone tissue, how it forms embryologically, the importance of calcium to healthy bone, diseases with bones, and how we repair fractured bones. So, with lecture 1, what I always like to do is kind of start with the basic functions of the system. So when we're looking at our skeletal system, we're looking at a series of bones that all interact. And then they're going to interact with muscles that we're going to talk about in the next unit. So the two units kind of become inherently linked to one another. And so when we're thinking about bone itself, it provides the major support for our body. And it provides major function. So if you think back on unit 1, we learned that there was a dorsal body cavity. And the dorsal body cavity was subdivided into cranial cavity and vertebral cavities, which contain your brain and spinal cord. And those are highly protected by a part of the skeletal system we call the axial skeletal system, which would include the skull and the vertebral column. And then when we look at the ventral body cavity, we divided it into thoracic cavity, abdominal cavity, pelvic cavity. And then when we look at that, the sternum and the ribs largely protect the organs of the thoracic body cavity. The abdominal body cavity is pretty much unprotected by bone. And then the pelvis protects key organs in the pelvic cavity. And so that protection is varied based upon the organ systems. And because bones create joints, and then muscles use the joints to create leverage to move bones, then muscles actually do the movement, but bones actually assist in the movement. And then one of the really key ions that our body needs is calcium. And we need adequate calcium not only to maintain healthy bones, but we need adequate calcium to make skeletal muscle contract, to actually make your nervous system work, and to make your cardiac muscle contract. And so what we do is we store calcium in our bone to make sure that we have a reservoir that we can draw from. And then if you go through a period where your blood calcium drops, you actually take it back out of your bone and put it back in your blood to maintain the function of those systems. So we're going to talk about that mechanism for mineral homeostasis and the role of calcium in a couple of things. And then we'll talk about it in detail in other units. And then blood cell formation. So one of the things that's critical is the fact that we have red blood cells, and that red blood cells carry hemoglobin. Because without red blood cells and without hemoglobin, we could not live on Earth with the relative amount of oxygen in our atmosphere, because it's only 21% of our atmosphere. And so the tissue that our body has that allows us to make red blood cells that only circulate for 120 days and then are destroyed, and at which we make about 2 million per second, all has to be highly protected against trauma. And so we protect blood cell forming tissue by putting it inside bone in what we commonly call red bone marrow. And that's where we produce our red blood cells and white blood cells. And then what we're going to see as we study the anatomy of bones is that all your long bones in your legs and arms are all actually hollow. And so the center part of the bone is completely hollow, and it's called a medullary cavity. And what we do in the medullary cavity is store triglycerides, so fat. So we started doing that before we were born, as we were making our skeletal system. We took fat out of mom's blood and stored it in our medullary cavities in a type of fat called brown fat that's real high in energy. And we did that so that after we were born, if mom was having trouble making milk for a while, we had this energy reserve we'd actually stored so that we could continue to have an energy source. And then we continue to do that throughout our lives and store triglycerides in that medullary cavity. So if you were an anthropologist or a forensic pathologist and you found a skeleton out in the woods, one thing you could do is actually cut the long bones open to see what the relative percent of fat is in the medullary cavity. And if you starve to death, you will begin to use up that fat, and it'll be different than if you didn't starve. So we can do that with animals as well. Okay. So what we started on yesterday was our skull, which is part of the cranial, which is part of the axillary skeleton. And so when we're talking about the axillary skeleton, we're actually referring to the skull, the vertebral column, and associated bones like ribs and sternum. And so that's what we're going to continue on Monday in lab and actually look at the vertebral column, ribs, sternum, and some other bones. And then next Wednesday, we're going to look at the appendicular skeleton, which is the skeleton up there that's the kind of tan or bone colored. So when we actually look at the bones in our body, if we look at the skull, we had 8 cranial bones that actually surround the brain and protect the brain that we looked at yesterday. We actually have 14 bones that make up our face. Okay. And then we have those 3 little dinky bones that we find in our inner ear we looked at, the inner ear ossicles. We have 3 on each side, so we have 6. And then we have 1 hyoid bone, which we're going to look at on Tuesday, which is a bone here in our neck, and plays a very important role for maintaining the relative position of your tongue and your larynx for respiration. And then on Tuesday, we're going to move into the vertebral column. And what we do is we divide the vertebrae down into regional areas of the body that we began to work on in the last unit. So the neck area is the cervical area. Then the area where the ribs are thoracic. The space between the ribs and the pelvis we learned last time was lumbar. And so we're going to look at cervical vertebrae, thoracic vertebrae, lumbar vertebrae, which are all very segmentally organized into individual vertebrae, so that we have 7 cervical vertebrae, that make up our neck that have to interact together so that we have flexibility to our neck. We have 12 thoracic vertebrae and 5 lumbar vertebrae. And then the vertebrae in the pelvic region form individually as individual vertebrae during embryonic development, but end up all fusing to greatly increase the strength of our pelvis. And so we have a sacrum, which is actually made up of 5 fused vertebrae into one bone we call the sacrum. And then we have a little tail that varies from 3 to 5 vertebrae in people, and those all fuse together. So we end up with one coxial bone, which is a fused one. And then when we look at the rest of the axial skeleton, then we have ribs. We have actually 12 pair, 24 ribs that all connect anterior to a sternum. So when we look at the axial skeleton, we have about 80 bones. But the good news is a lot of them are paired in the left and right sides. So they're not really 80 bones to learn. So what we're going to start working on next Wednesday are the bones that connect your appendages to the axial skeleton. So traditionally they've been called girdle bones. And so what we do is we divide them into the bones that connect the arm to the axial skeleton. So those are pectoral girdle bones. And on our back we have 2 scapula, which are fairly large, very flat bones. And then anteriorly we have a bone that we can palpate right here, which is our clavicle. And those 2 bones, along with muscles and tendons and ligaments, are what connect our arm to our axial skeleton and keep it attached to us. So as we move into the upper extremity, our arm, we have a very large bone up here called the humerus. Then we have 2 bones in our antebrachial area, the ulna, which is what forms your elbow, and then the radius, which is designed to allow your arm to rotate, hence the name radius. And then as we move into the wrist, we have bones that we call carpals. And so we actually have 8 in each wrist, or 16 bones. And we'll learn the name of each carpal and the order in which they occur. And then as we move into the hand, the manus area, we have metacarpals that form the palm side part of your hand, and then phalanges that form the fingers that we'll look at. So 5 in each hand for metacarpals. So as we move to the lower extremity, then the upper extremity is the pectoral girdle. The lower extremity is the pelvic girdle. And we have 2 really large bones to the side that we call the os cox. And they actually come together anteriorly to form a pubis, but they depend on the sacrum posteriorly to attach it to the axial skeleton. So you can kind of see that up there, how they come together anteriorly, but attached to the sacrum posteriorly. And then as we move into the legs, the pattern's going to be the same. The upper leg has 1 large bone. So our largest bone in your body is the bone that's in your thigh, the femur. As we move into the lower leg, we have 2 bones, just like we had in the lower arm. So the tibia is the really large bone that supports most of your weight. The fibula assists it. And then we have a patella that protects our knee socket anteriorly. So our kneecap is the patella. And then as we move into the ankle, then the ankle bones are called tarsals. And then the same pattern that we saw in the hand, then the long bones of your foot that form the long portion of your foot are called metatarsals. And then the phalanxes or phalanges will form your toes. So over the course of this week and next week, we're going to go through all those bones and learn different names on the bones that we'll revisit in the future of the class as we talk about muscles, where nerves go, where blood vessels go. So what we always like to do is we always like to put things in categories. They're kind of like filing cabinet drawers. So when we take all our bones, we can divide the bones into long bones. And the long bones are pretty much limited to our appendicular skeleton, arms and legs, or extremities. And then we have short bones, which the examples would be the wrist bones and the ankle bones are short bones. We have flat bones, so a good example would be the sternum, which is an incredibly very flat bone midline that attaches the ribs anteriorly. And then vertebrae have real irregular shapes to them, and they vary between cervical vertebrae all the way to lumbar vertebrae. And we're going to use that variation to be able to distinguish between a particular vertebrae as being sacral, cervical, or lumbar. And so they're called irregular bones because of that variation. And then our kneecap, or patella, is a unique type of bone, which is an ossification of a ligament. So when you're born, you did not have a kneecap. It was actually still a ligament connecting bones together. And then as you maturate, the ligament becomes ossified over time. And so any bone that's an ossification in a ligament is called a sesamoid bone. The most common one we have is our patella. Almost everybody has them associated with their big toe, and a lot of people have them associated with their thumb. And so we have a number of sesamoid bones and some vary. So this is an example of a sesamoid bone associated with the thumb. So the most common place we make them is between the joint between the proximal and the distal phalanx and on the palmar surface. So if you feel this, sometimes you can find a little round bone like that, find that you can roll around. And that's actually a little tiny sesamoid. And so this is a good example of it. No. And usually they're more prominent the older you are. So what we did yesterday is we looked at sutures, and we talked about how when babies are born, the sutures aren't in place so that the skull can grow with the brain, so mom doesn't have to pass adult-sized skull through the vagina as the baby comes out. And so what eventually happens is the bone plates and the skull grow together in an overlapping pattern that we call sutures. And for some reason in people, little bone islands will form in the suture, so that you have a suture plane with a bone in it. So you can actually see 3 in a row on the back of this skull in the lambdoidal suture. And they're called Wormian bones. And so they're bone islands, and they're highly varied on skulls. So there's 3 right in a row right here. There's actually 2 over here, a 3rd one over here. This skull actually has a lot of Wormian bones, where the ones we were looking at only had a few. And if you were to look at it, if you had the chance to look at a whole bunch of different human skulls, real skulls, then you'd find a real varied pattern to Wormian bones. The problem we have, because plastic skulls are more pliable and don't get broken up as easy and a little cheaper, is that plastic skulls are all made from one model. So there is a repeated. It's like looking at the same skull all the time. So we don't see the variation. So that's why I get the real bones out for you to look at, so we can see the variation. So I spent a little time going through terms that are on your bone list, because the terms have been used specifically as a description of a characteristic of a bone. So these definitions are actually on the 2nd page, or on the 3rd page, which would be the 2nd full page of your study guide, where there's actually a list of terms. And so what we're going to do is, so it's on this 2nd page on your study guide, where the terms are spelled out for you. And so when we're looking at long bones, then all the long bones articulate proximally with another bone. So the word articulate means to interact with or create a joint with, right? And so, and our biggest bones that connect our appendicular skeleton to our axial skeleton, so the humerus in the arm and the femurs in the leg, actually have the largest big round processes for articulation. So a very large, round, flat, really rounded surface for articulation is called a head. And so we're going to see that the humerus has a fairly large head, and then the femur itself actually has even a much larger head. So heads allow for the greatest range of motion, and that's why where our appendages are attached to the axial skeleton, heads exist. So a head allows you to move on this plane, to move on this plane, and then to actually move on a 3-dimensional plane all the way around. And so the heads in your femur and your humerus are critically important for giving you the greatest range of motion within the appendage. Compare that to your elbow. Your elbow is only designed to move on this plane. And so you have a much more limited range of motion in both your knee and elbow. Right? So if you have a head, then if the bone tapers underneath the head, then we call that tapered area a neck. So the neck we looked at yesterday was on the mandible. And so we said one up here was the condylar process of the head of the mandible. And then the narrowing below that is a neck. So what we're going to see when we look at bones in the future is that the humerus actually has 2 necks. And the femur has the most pronounced neck, so that's obvious when we look at it. So when we look at necks, we see that. Then generically, the biggest part of the bone can be referenced as the body. So we did it yesterday in lab with the mandible, saying that this portion of the mandible is the body. So on any long bone, the middle portion of the bone, we can just refer to as the body. So you end up with a head, neck, and body on the bone. All right, so with flatter bones, what we have is we have bones that change direction. So where a bone changes direction is an angle. And so this is the scapula that sits on the back of your shoulders. And so we actually have this piece of bone on this angle, and then here on this plane, the hair changes and runs this way, and at the top it changes and runs across. So this is an angle where the bone changes direction from here to here. And so what we can do then is use descriptive words that we worked on yet last time as ways to draw references to things. So this is the way the scapula would sit on you. This would actually be a left scapula on your back. And so since the really big angle points downward, then it's said to be the inferior angle. Since the opposite angle actually points upward, it's said to be the superior angle. So if we have a bone extension off of an angle, then it's called a ramus. So the one we looked at yesterday this was the body of the mandible, and it's running on this plane, but then all of a sudden the bone changes and goes to this plane. So this becomes an angle, the angle of the mandible, and then this bone extension beyond the angle is a ramus. So the ramus we're going to learn are one in our mandible and then one in our pelvic bones that form the front of our pelvic girdle. We'll have ramus on them where they change. So if you ever, yes?
Is there not a ramus on the scapula? Since it goes three different directions?
Yeah, but we don't. When you look at your list, you think you're learning everything about bones. You're not learning most of what an orthopedic surgeon is. So yes, but they're not on the list because most of the occupations that go through this class don't need that. But yes, you're wrong. So what we do with flat bones, or bones that have very pronounced edges, is that we call an edge a margin. So the margin of the mandible would be this edge of the mandible right here. So our scapula, because of the way it sets, actually has very predictable margins or borders. So since this is a left scapula, which would be a knee like this, and this points toward the armpit, so we call it the axillary border. This one would actually point toward your vertebral column, so we're going to call it the vertebral border. And that allows you to actually think about how the bone is organized on your body by actually labeling these so that they're descriptive to direction. So when we look at joints, then we've already talked about head. And the key to the head was it provided range of motion on three different unique planes. So 3 planes of motion. As we move away from heads, we have rounded surfaces that are rounded on more of a single plane than multiple planes. And a real rounded surface that would create a joint that has more limited motion is a condyle. So this is the end of the femur, and this is part of the way in which your knee is constructed. And so in your knee, you have these 2 really big rounded surfaces that allow you to do this with your knee. And if you actually do other things with your knee, you end up with knee surgery. So your knee is really designed to only have one range of motion. That's what the condyles provide. And so what we do is we look at the femur and we use anatomical position. And we say, well, the one closest to the midline would be the medial condyle. And the one on the opposite side of the bone would be the lateral condyle. And again, that helps us figure out the orientation of the bone because we're using directional terms to describe it. All right. So usually what keeps joints together are ligaments that go from bone to bone to prevent the joint from being pulled apart. And then we also have muscles that attach and their tendons attach. So because the attachment of a ligament or a tendon needs to have a fairly strong attachment, then the more stress there is on the joint, the larger the surface area of attachment needs to be. So usually what we see toward the ends of long bones are these elevations associated with the condyle. but a condyle is a flat surface that would occur in the joint for smooth movement. Epicondyles are enlarged roughened surfaces used to attach muscle and tendons and ligaments to each other. So this is the elbow, and the bone you're looking at would be a right humerus. So it would be my elbow like this. And so the real flat surfaces here are condyles, and they allow you to create this motion. But now if you feel right here by your elbow, there's a really big bump there that you can palpate on the inside. And that really big bump is your medial epicondyle. It's this big bump right here. That's for muscle attachment. So a lot of the muscles that are actually going to be used to manipulate your wrist and fingers are actually attaching to that process. So we'll talk about that in the next unit. So epicondyles are designed for attachment of ligaments and tendons. So if we went back, if that makes sense to you, and if we go back, these are condyles. So what are we going to call this roughened area right here, and this roughened area right here? Epicondyles. All right, so the other thing we can have on flat bones, the shafts or bodies of long bones, is elevations. And the elevations, again, provide increased surface area for the attachments of largely tendons that are associated with muscles. And so what we try to do is use a vocabulary that's descriptive of an elevation that's not very high, an elevation that's higher, than an elevation that's really high. And so what we use is line or linea in Latin, crest or crista in Latin, and then spine. And then the pattern is that lines are smaller elevations that don't arise as high on the bone. Crest or crista is a higher elevation on the bone, and spines are the highest elevation. And so by doing that, we're trying to be descriptive of what you should be looking for. So if you're looking for a line, it can be very subtle. But if you're looking for a crest or a spine, then it should be very obvious. So the difference. So on the back of your femur is a long line that starts near the proximal end and runs all the way down the back of it. And it's designed for the really big muscles on the sides of your thigh here to actually attach to. And so it's called linea, the line, and then aspera. So the linea aspera is a line that goes all the way back on the back of the femur. And then what we'll see is that the more muscle mass you have, the more pronounced these projections are. So if you look at somebody with very thin thigh muscles, then this line is going to be very, very subtle. And if you look at somebody with enormous thigh muscles, then the line is going to be much more prominent. And we actually remodel our skeletons based upon how much muscle mass is actually present.
Does the aspera have any meaning?
Yeah. I was trying to think that through while I was talking. I haven't found the top of it, right? That's not. So, if I don't think of it as I'm talking up here, I'll get back to you tomorrow or Monday. All right. So a crest then is a higher elevation than a line. So the one we looked at yesterday was on the ethmoid bone, and it's a projection upward that actually goes up between the two frontal lobes of your brain a little bit. And so it was called the crista galli, and it was midline in relationship to the frontal lobe on the ethmoid bone. So one of the biggest spines we have in our body is actually on the scapula, and you can actually palpate that on somebody or palpate it on yourself. And it's a big ridge you can feel right here. You can actually kind of take a little triple on it because it's very long. And it's, again, going to be designed for some of the really large muscles that we use to move our shoulder to attach to. All right, so this always reminds me of Sesame Street, the T words. So we have words that are designed to attach muscles and ligaments to. They're typically associated with heads on bones. And so tubercle, tuberosity, and trochanter, the three T words. And that's the order of their size. So tubercles are considered less large relative to the bone and the head you're talking about. Tuberosities are a little larger, and trochanters are gigantic. Okay? So your humerus, if you stand in anatomical position and you palpate your shoulder, there's a big rounded process to the lateral side. And that's the one that's actually not labeled up here, but it's the one on this side over here. And that's the greater tubercle. And then as you go toward the medial aspect, little right in here, there's a smaller one. And that's actually the one that's labeled up there called the lesser tubercle. So your humerus actually has two of them on it. One of them larger, one of them smaller, so we denote it by name, lesser and smaller. Tuberosities are larger elevations, but remember what I said. They were relative to the bone that we're talking about. So the bone we're looking at here is the radius, which is the bone that allows you to rotate your arm like that. And the top of it we're looking at, where 1 and 2 are labeled, are actually where it would articulate in your elbow. So that real rounded surface at the top is a head. The narrow below the head is number 2 would be a neck. And then what we have on the anterior surface right here is this enlargement, which your big muscle in your upper arm, the biceps, actually attaches to. So this has to have a great enough surface area so that when your biceps contracts, you can actually pull your arm up, even with weight in it, so that you don't just pull the tendon right off the radius. And people actually do that. Weightlifters with real heavy weights can actually pull the tendon clear off their radius. And so it's called the radial tuberosity because it's larger. So the largest tuberosity you have in your body is what you're sitting on. There's 2 bumps where you sit. And if you sit too long, it's like, ow, this is starting to hurt on a flat surface. Those are the biggest tuberosities in your body, which would be the ischial tuberosities. So there's only one bone in your body with a trochanter, and that's your femur. And the trochanters are designed to allow the largest muscles in your pelvic region, your gluteal muscles that form your buttocks area, to actually attach to. And they're very large muscles, so they need an amazing surface area because they're constantly moving the weight of your body all the time. And so we actually have 2. So on the lateral aspect right here, we have a greater trochanter. And then medially and posterior, we have a lesser trochanter. And the trochanter is one of the things that explains the difference in the shape of women's pelvis and men's pelvis when you're looking at them walking, because to widen the birth canal so babies can come out, women's pelvis is remodeled and the trochanter gets pushed more laterally. So that's why women have a bump here that's more obvious than men. Because men don't give birth, then their pelvis isn't widened and the trochanter is actually slightly more anterior. And that's actually why if you look at a woman walk or run, their gait is slightly different than a man's because of the orientation of the trochanter. So a hamulus is a hook. And so we actually have one bone in our wrist, and you can palpate it right here on your little finger side of your wrist. There's a bump there. And what actually happens is that bone actually has a structure that goes up and hooks over. and then tendons go under it. Okay? And so the bone is going to be called the hamate. And the bone's name comes from the fact that it has a bone, which is called a hamulus. So the bone name is directly related to the fact that this book exists. So yesterday we began to work on the names of openings. And so the one we saw frequently in the skull was the word foramen. And so anytime you see the word foramen, it just means a hole in the bone. Right? So what we're going to see as we go forward is that there's some differences in the way in which Latin and Greek change words from singular to plural. So we're used to, in English, of adding an S or an ES to the end of a word, and that's not what they do. So it's not foramen with an S if it's more than one. It's foramen. And so they change the ending of the word. So we'll talk about that in lab because we'll have a couple of places where we use the word. Right? So a foramen is a hole. So the biggest hole in your skull that we learned yesterday was the foramen magnum. The word magnum means large. The largest foramen in your body is actually in your pelvis, through which muscles and some things actually pass. And so it's called the obturator foramen. So that's actually the largest foramen in your body on any bone. So if we wanted to denote a hole that looks more like a tunnel, then we convert the word from foramen, which just simply means hole, to meatus. And then a meatus is a reference to a canal or a tunnel. And so the hole that goes into our inner ear is technically a meatus. So this is actually technically a meatus. So we call it the external auditory meatus because auditory tells us it's associated with the ear. But because we have two, one inside the skull and one outside the skull, then we have to distinguish those, so external and internal auditory meatuses. We'll also see meatus used for soft tissue as well as we go forward, and not just a canal in the bone. So it can be used for canals that are soft tissue as well. So a fissure is an elongated opening. So the fissures we looked at yesterday were actually in your eye. And so we had one on the superior aspect of the orb of the eye, so we called it the superior orbital fissure. Then we had one in the inferior aspect of the eye, so we called it the inferior orbital fissure. So again, what we're doing is we're using one of the directional terms that we use. We're using a descriptor where you'd be looking the orbit of the eye. And then we're trying to tell you that it's an opening that's elongated instead of round or tube-like. So a fissure. And then yesterday we worked on sinuses. And as far as the skeleton is concerned, most of all of our sinuses are in the head, where they play several functions in terms of lightening your skull, providing sound chambers that change the quality of sound, and a couple of things. So the ones we looked at, one example would be right above your eyes here. In the frontal lobe, we have a frontal sinus. So yes?
Are sinuses open to the, I suppose, outside world, or what?
No. Well, indirectly. So the paranasal sinuses associated with your nose are indirectly open to the outside world because they have openings to your nasal passage. The other sinus we did, which was the mastoid sinus back here, has no opening to the outside.
I guess I'm asking if they're pretty much enclosed in whatever they're enclosed in. Okay.
Pretty much enclosed in bone. Correct. All right. So depressions are things where there's a lower area in the bone, and so the most general term we can use for a low area of bone is a fossa. So a fossa literally is a depression. So we're going to learn a couple on the scapula where muscles set. So the supraspinous fossa and infraspinous fossa. And the reference point is the spine. So the supra is above the spine, the infra is below the spine. And so again, descriptive words in terms of direction. Spine is the reference point, and then their fossas. So if we have more distinct ones that aren't just general depressions, depressions in the bone, then we call them impressions. And impressions have been critical to our understanding of anatomy from just looking at bones, because largely impressions give you the exact size and shape of the structure that created. So essentially yesterday we were looking at the impressions created by blood vessels in the skull. We were looking at the superior sagittal sulcus, the transverse sulcus, and the sigmoid sulcus. But one of the ways we've been able to look at in an anthropologic standpoint, look at ancient skulls and try to figure out changes that have occurred in brain function and shape when there is no brain left, is by looking at the impression of the brain on the inside of the skull. And so inside of the skull, you can actually see the exact shape of the cerebellum, see the exact shape of the occipital lobe of the brain, the exact shape of the temporal lobe of the brain, and the exact shape of the frontal lobe of the brain, all in the floor of the skull. And those are all impressions. And it gives us shape and size. So it gives us a way to actually look at soft tissue that's no longer there and get a view of it. So typically if we have a depression in the margin of a bone, then we call it a notch. So the one we looked at yesterday was the mandibular notch, which was this depressed area here between the mandibular condylar head and the coronoid process, which is number 3 up there. And in the word we just used, the sulcus is a depression that is like a groove in a bone. So it's an elongated impression in the bone. And so we looked at the sulcuses in the skull yesterday. And then you actually have a pretty pronounced one. So again, if you're in an anatomical position, you find your greater tubercle and move over a little bit right in here. Then you actually have a groove that the tendon from the biceps passes through to actually attach to the scapula. And so it's called the intertennacular sulcus because it's between the great and lesser tubercles of the humerus. And actually in a clinical context, if that tendon is irritated, if you actually push on that on somebody, they'll go, ow, because it's real tender. So we can actually learn about things that are going on with muscle by palpating. But to do that correctly, we have to know the landmarks, which is why we learn bone. So that's kind of a summary of all the terms you're going to see embedded in names on bones. So my goal is, with this, is that now that if you see the word meatus, you'll think to look for a tunnel. So it tells you what to look for. So now what I want to do is I want to go back and look at your appendicular skeleton and your long bones. And with long bones, we have a set of vocabulary that's unique to long bones. Okay? And it's more specific than the general terms that we just did. So the general terms we just did on long bone would be the upper part would be called a head because it's really big and rounded. Under a head we'd have a neck, and then the major portion of the bone would be a body. Those are kind of generic outside view of the bone. And so when we begin to think about the functionality of the bone, how the bone interacts in the joint, how the bone was constructed embryologically, then we use much more specific terms for it. So what we're going to do is we're going to use terms that directly relate to how you form these bones. So when you form a long bone, the area where bone begins to form is called a center of ossification. Then the center of ossification is midway on the length of the bone. And so that piece of bone that develops first is referred to as the diaphysis. So the diaphysis is actually the body of the bone, but what it describes is that developmental sequence that actually occurs. So that the diaphysis is always the first portion of the bone to become ossified. And within all long bones, the diaphysis is going to be hollow. And the fact that it's hollow allows us to store adipose tissue in that area for energy reserves. So the diaphysis is always hollow, and what it contains is a medullary cavity. And in the medullary cavity is where we store what we would call yellow marrow, which is largely fat. So if you go to the grocery store and you go to the meat market and you look at what we commonly think of as a round steak, a round steak is a cross-sectional cut through the thigh of a cow. The bone in the middle that's round is the diaphysis of the bone, and that real spongy, whitish, kind of buttery looking stuff on the inside is yellow marrow. And so that's become a delicacy in some high-scale restaurants where they take the diaphysis of the bone, cut it with a saw in between, lay it open, and then season the marrow, cook it, and then it comes out and you eat the marrow out of the bone. And it's got the consistency of warm butter. And then what's kind of interesting to that is that the native populations of the Arctic, that in the United States we call Eskimos, for years have depended upon marrow as a very, very important high energy food source to stay alive in a very harsh environment. So we're just kind of catching up with their culture. They've eaten for years. Okay. All right. So what happens is the center part of the bone is what begins to develop first. And so what we end up with then, as you're developing your long bone, is this piece that's beginning to develop. We call the diaphysis. And then it begins to hollow out so you can store energy from on, right? Then what happens is we end up with a second piece here that begins to ossify, and a second piece here that begins to ossify. So the next thing is the two ends of the bones begin to ossify. And in your large bones, this is incomplete when you're born. And you haven't even finished this process. So the ends of the bones are called epiphysis, because they are a secondary center of ossification. And then what we use is directional terms to describe which epiphysis we're talking about. So the one at the proximal end, which would be closer to the axial skeleton, where the head would exist, is the proximal epiphysis. And then the other end of the bone is the distal epiphysis. So it tells us directional terms. Now, the epiphysis, coming from a developmental pattern we're looking at, also is the correct name for any long bone. And not all long bones have a head. So the proximal epiphysis is true of every long bone. So what eventually happens is we're actually born with a piece of cartilage here that we call a growth plate, generically. And we have one at the end of each bone. So since we're born with a growth plate, the point where the growth plate exists is called a metaphysis. What's eventually going to happen as you reach your adult size is the cartilage is going to go away. You're going to end up with a line of bone there that we can actually see. And so at the top, You can actually, I'm not tall enough to reach it. I'll do it. At the top here, you can actually see this line right here. It's called the epiphyseal line. That's where the old growth plate was. And we can actually look at x-rays of a teenager and know whether the teenager has any growth potential left or not, as the growth plate converts to a line. And that typically is completed in women by 14, 15, and 16, and it's not completed in men until 18, 19, or 20. So there's actually a phase shift difference between men and women on this process. So then the end is any long bone is going to have a proximal and distal epiphysis, a proximal and distal metaphysis, and only one diaphysis. Okay. And then what we'll see is a different pattern inside. So only the diaphysis has a medullary cavity where we store yellow marrow. The metaphysis and epiphysis have a type of bone that we call spongy bone that you can see at the top of the figure up there. The spongy bone is how we protect our blood cell forming tissue. So what we would see in spongy bone is what we would call red bone, which is involved in production of both red blood cells and white blood cells. All right, so the rest of this I'm actually going to use in lab as we go through lab, where we actually have the bones to look at while we're doing it. So if you want to review stuff from the lab we did yesterday, here are the fontanelles we looked at yesterday. And then what I did is I took a picture of a bone, I took a picture that's labeled and put it beside it. This is a great way to quiz yourself. Do you know what 3 is called? Do you know what 1 is called? Do you know what 2 is called? So they're numbered, and then here's the answers. Okay? And so, and this we're going to use on Tuesday in lab, so bring this. And I did the same thing here. So I just reversed the order on it. So here's a skull. There's a bunch of numbers on the skull. Here's the names of everything. So this is the way you quiz yourself. Can you name everything that's numbered on it? Some of the things you don't actually need to name. I tried to get pictures that are pretty well matched. So different aspects of the skull that you can see. And so those are all good ways to review. Then we're going to look at the difference between male and female pelvises next Wednesday. So make sure you bring this to lab on Monday and Wednesday. So what we want to do is we want to now kind of turn our attention to bone tissue, kind of how bones developed while you were going from a single cell to a neonate when you were born, and then how you continue to develop from a neonate to your adult size. And for all mammals, where the baby has to come through an opening to the outside of the body, then it's critically important that the baby's not adult size. Because it would make it very hard to get out of the body. And so in most mammals, then we have this growth pattern that actually exists. And so we're going to talk about that. And then we're also going to talk about the physiology by which we manage our skeleton. And then we get to talk about clinical diseases that we see in skeletal material as well. So I just want to go back and remind you that bone tissue is another type of supportive connective tissue. All right. And so when we look at the skeletal system, we're going to see quite a bit of different types of connective tissue in it. So we're going to see cartilage, and the most common cartilage throughout our skeletal system is hyaline cartilage, and it's in every joint where you have free range of motion. And the hyaline cartilage lines the end of bones, and provides a very smooth, lubricated surface for which we can make movements. So as you age, you can undergo changes in those joints through osteoarthritis or rheumatoid arthritis. And the end product is a lot of pain in moving joints because the cartilage has been altered in the joint, and therefore we get increase in friction, which decreases movement and increases pain. So we start out our life with lots of really nice, good hyaline cartilage. And because hyaline cartilage is non-mitotic and it doesn't repair itself, we end up through time with worn cartilage. So bone itself is a unique type of connective tissue that's designed to have a very dense matrix to give bone its characteristic hard shape. Right? And then inside of bone, in open spaces in bone, we have bone marrow, which is either adipose tissue or red bone marrow, which are connective tissues designed to store fats and or produce cells for us. And then all bones are lined on the outside with a layer of connective tissue and a layer of epithelial tissue. And so this outer combination of tissues, epithelial and connective, that cover all bones is called the peri, because it's around the bone. And oste is a reference to bone. So anytime you see the word oste, O-S-T-E, incorporated into something, it's a reference to bone. So the disease, osteoporosis. Porosis, porous, or pores, or holes, bone. So it literally translates to bones with big holes in it, which is what it is. So, all right. So bone tissue can be referred to as osseous tissue. It makes up most of our skeleton. And remember, when we looked at connective tissue, we had cells, and the cells create a matrix that's around them. It's made up of a round substance and fibers. And typically what we do is we use a prefix for the name of the cell that tells us the type of connective tissue we're talking about. So in true connective tissues, fibroblasts, fibrocytes. As we move to cartilage, we change fibro to chondro, and we had chondroblasts and chondrocytes. So we're going to see the same thing in bone. We're going to have a blast that denotes an immature cell making tissue. We're going to have a site that denotes a mature cell maintaining tissue. And we're going to use the prefix that tells us it's bone, which was oste. So it's going to be an osteoblast and an osteocyte. Okay. So just a pattern that we constantly use. So what we need to make new bone all the time, and we remodel our skeleton throughout our life. Unfortunately, we get less good at doing that as we age. And so we see more broken bones from falls in elderly people than in young people because the process of remodeling bone slows down as we age. But to remodel bone, to repair broken bone, you have to have a stem cell that can give rise to new osteoblasts. So when we talk about stem cells, we talk about stem cells that can give rise to anything. And so we use the word puri in front of it. So pluripotent stem cell is the stem cell that can give rise to anything. And if you've been reading the news or listening to the news, somebody just won a Nobel Prize because of their work with pluripotent stem cell. And so if a cell can't become anything, then we call it a unipotent stem cell, meaning it can only become one thing. So osteogenic cells that develop into osteoblasts are an example of a unipotent stem cell. And we keep them in our body throughout our life so that if we damage bones, we can repair them. If we put on a bunch of muscle mass, we can remodel the bone and tolerate the increase in muscle mass or the force on it. And so osteogenic cells are stem cells that develop into osteoblasts. Well, osteoblasts form bone matrix. So obviously when you were young and you were growing in size, you had tremendous activity of osteoblasts that allowed you to increase your bone length. Right? And then once the bone matures, we convert the cell converts from an osteoblast that forms bone tissue or matrix to a cell that maintains the tissue. And that's an osteocyte. All right. So one of the things that's unique about bone compared to the rest of the connective tissues is we have to constantly repair and replace bone because osteocytes age. And so we constantly remodel our skeleton. So to remodel a skeleton, you have to have a bone that breaks down existing bone matrix. So osteoblasts can make new bone matrix. And so in this instance, the cell that's going to break down bone matrix is called an osteoclast. So the ending class is going to become important to your understanding of that process. So anytime I say the word osteoclast, I'm referring to a cell that's actually going to degenerate bone matrix, break it down. And we constantly do that all the time, constantly remodel our skeleton. We get worse at it with age, which is why elderly people have more fractures than they fall in.
So the holes from osteoclasts, there's lessons that's not unique in the bone?
Well, it just so happens that what's really cool is that the hole created by an osteoclast is about the same size as the hole we need to make the new bone that's going to fill it in. So there's a real cool coordinated pattern. We're going to come back and talk about that. I can actually show you some images that will help that make sense more. Right. So let's talk about the extracellular matrix. So we have cells, osteoblasts, osteocytes, and they secrete a matrix. So when we did connective tissue, what we said was the matrix was a fiber, and so we could have elastic fibers, we could have reticular fibers, and we could have collagen fibers. So as we went from true connective tissue to cartilage, in particular hyaline cartilage, the matrix became dominated by what type of fiber? Collagen fibers. And that's the exact same case in bone. As you move towards sporty connective tissues, collagen is a very strong fiber, and that's what we need to make bone matrix strong, is collagen fibers. And so what we do is we call that protein component to the matrix the organic matrix. The organic matrix is largely 95% collagen fibers, and then about 5% ground substance, which is chondroitin sulfide. Okay? And so we also, in bone, which is unique, crystallize minerals. And the crystallized minerals form the shape of little tiny bricks. And then the little tiny bricks are held to the fibers by the glue, the chondroitin sulfide. And so bone is very dense because we take calcium, we combine it with a carbonate molecule and create a compound that's largely a type of calcium carbonate. And that's what makes bone really strong. Okay. So we call that the mineral salts matrix. And the calcium phosphate crystal we produce is called hydroxyapatite. And so hydroxyapatite is critically important to creating the kind of bone matrix that we have. And what we wouldn't want is the enzyme that's coded on DNA for you to make hydroxyapatite to be activated in other types of cells, because then we would crystallize other types of tissue. So there's a very rare disease that a young gal recently died from, where the gene for making hydroxyapatite got turned on in skeletal muscle. And over the course of 4 or 5 years, she completely ossified all of her skeletal muscles. And then she could no longer move, breathe, and die. I can't, I was trying to remember the disease name. It's very, very rare. Doesn't happen very well. I'll have to look it up. Okay. So what's kind of cool is if we're exposed to other things, we'll also incorporate other things into that crystalline matrix. So gold is one that we do. So if there's gold in drinking water or anything that you're ingesting, then you'll actually take the gold and incorporate it into the bone matrix. So in some high-tech restaurants, they actually use little shaves of gold to adorn food that you eat. And then when you eat the gold, you incorporate it into your bone matrices.
It's in your bones.
Pardon?
Gold hunting is in your bones.
Yeah. So you could actually, in areas where there's a lot of gold in streams, people who live there all their lives, you could actually extract gold out of their bone material. So dentists have always known that, and caps on the inside are gold, because the gold helps the cap bond to the tooth, as it says, a modified type of bone. Right? So we also do lead, and that's not a good thing. So, but in Spokane and northern Idaho, it's been a problem. So the wealth that created Spokane came from silver mines in northern Idaho. And what they did is they took all the rock that they extracted the silver from and dumped it into streams. And one metal that's always common with silver is lead. So they actually contaminated most of the waterways in this area with lead. So if you go to Harrison, Idaho, where the Coeur d'Alene River dumps into Lake Coeur d'Alene, there's some of the highest lead contamination of soil in the United States. And birds, like swans and stuff, will fly in there. They muck in the mud to find little worms and stuff. And if it's a cold spell where they stay too long, they die from lead toxicity. And so there was a lot of problems that were noticed in children in northern Idaho. So this epidemiologist from Harvard came out and did some research, and he actually found some of the highest lead levels in human bone ever recorded in some of the children in Wallace and Kellogg, Idaho. So now when you drive on the interstate and you're going through Kellogg, there's this giant berm that's south of the road. There was a big tarp over it. Now they've got a soil line. What they had to do is remove most of the soil from the yards and actually put it in that pile and try to take all the lead that the children were being exposed to because of all the soil got contaminated.
So does it stay in your bones then?
That's the dilemma. So in children, because children are producing bone during growth periods at an alarming rate, at rapid rates, then largely once the lead is removed out of the blood where it's highly toxic, then it goes into your bone where it's less toxic. But unfortunately, as you age, and if they enter an osteoporotic event where they begin to break down bone, then the bone's going to be returned back to the blood. And that's the biggest concern. All right, so just an example. And the other things we could see is we got the great idea to use atomic bombs. And so we went to test them. So we tested them in the Arctic, and we tested them on a great island chain in the Pacific where a swimsuit comes from, the Bikini Islands. And we actually made the islands uninhabitable because they're highly contaminated with strontium and plutonium. So what we have in populations, so one area we did it in continental United States was in New Mexico. And it's an area called Great White Sands, New Mexico. And we actually exploded atomic bombs. We actually put GIs in trenches at different distances from the explosion and actually exposed them to strontium and nitrogen and plutonium. And now we can actually quantify bone cancer events that have occurred since that event. It's actually a woman who wrote a book whose family owned a big ranch near there. And the name of her book is The One-Breasted Clan, because every woman from the time the atomic bombs were used has had breast cancer. Grandmothers, daughters, granddaughters, great-granddaughters have all had breast cancer.
Radioactive stuff into development fetus.
Yeah. So what's interesting about plutonium is that they divide by half-lives. So, and half-life is unique. So the half-life of plutonium is 270,000 years. For plutonium to become safe, you have to go through 5 half-lives. 5 times 270,000 years. So if you listen to the news, we have all kinds of plutonium contamination in the Tri-Cities and Hanford. So how long are we going to have to store that as we clean it up? 5 times 270,000 years. So what happens is this stuff emits radiation in the form of different radiations. So we have alpha, beta, and gamma. Alpha radiation is real low energy. Your skin protects you from it. Bounces right out. The radiation we use to do x-rays is beta radiation. The people who do the x-ray don't stay in the room with you. They go into a room and there's a thin layer of lead in the wall so that it bounces off. And so if you're getting, like, you know, the dentist, they put the apron on you when they do and it's real heavy because it contains lead. They put it on you to protect your ovaries if you're women and testes if you're men, so they're not exposed to radiation. Gamma radiation just goes through you like you don't exist. So what's fascinating is beta radiation bounces off bone, but it goes right through your soft tissue. That's how X-rays work. Gamma radiation, you wouldn't see. It would go through everything. But what happens is, if it's inside you and it radiates, because these are wavelengths, it hits DNA. And we talked about this with UV. It causes DNA to
mutate,
break up. And that's what leads to cancers that we see largely associated with radiation. So you probably have heard of Madame Curie, which was the woman who did a lot of work with radiation. And do you know why she died? Radiation exposure and cancer. All right. So what actually happens is if we look at the organic matrix and the mineral matrix, it changes with time. So children, it's 50-50, which is why children's bones are so pliable. And as we get to an adult, then it changes about 33 to 66. So this is organic matrix, this is mineral matrix. So as an adult, it changes to 33 and 66. As we age, it continues to drop, so it goes from 33 and 25 to 75. That's why elderly people's bones are more brittle, and that's why they break more easily, is the crystalline material is becoming more common. And the key to having bones that can be pliable is the collagen, and the collagen concentration is dropping. That's why bones become brittle with age.
So doesn't that mean they also have a greater reservoir of calcium?
Pardon?
Doesn't that also mean they have a greater reservoir of calcium?
It does, as long as we can extract it back out.
Oh.
But we don't get as good with that anymore. So. All right. So that's kind of cool. So here's something you could do if you if you took like a chicken leg bone and you stuck it and you got some vinegar, which is an acid, and you took a jar and you took the chicken leg bone in the jar and you poured the acid over it, but don't leave it for a long period of time without changing the vinegar every once in a while, because things will start growing and it starts smelling really bad. So about every other day you have to put new vinegar in it and get rid of the old vinegar. Then what will happen is the vinegar, because it's an acid, is going to demineralize the bone. It's going to dissolve all of the hydroxyapatite crystals, and you'll end up with a bone that's largely hyaline cartilage, like hyaline cartilage, and you can actually tie it in a knot. It's very, very pliable. So when your dog or cat eats bone, it's exactly what their stomach does. It demineralizes the bone. They use the calcium then to their source of calcium. And then they can use an enzyme then to break down the collagen. You can do the same, it just takes you longer than the dog or cat because your acid in your stomach isn't quite as strong. So if you do something different, if you take a chicken bone, like a lug bone, and you stuck it in your oven and put your oven on clean, so that it's at a high temperature for a long period of time, then what the high heat is going to do is destroy the organic matrix and destroy the collagen. And then if you take it out and just tap it, all the crystals will just come apart. And you'll just end up with a pile of little crystals. That's actually what happens when we actually cremate. Is the high heat takes all the water and destroys all the protein, and the remains we get are largely the uncombustible crystalline compounds in the bone. So you can go from this size to a little box. There's all your protein and water. Okay, let me do this and then we'll be done. So we already talked about it indirectly. So we said that the inside of the epiphysis and metaphysis were filled with a bone that had lots of holes in it. So we call it spongy bone. And then spongy bones where we store bone marrow. So the surface of all bones and the diaphysis of bones are made highly dense without any openings in it, big openings in it. So we call that compact. And so the surface of all bones is compact bone, and then the diaphysis of all bones is compact bone, of long bones. And then in the ends, we have a veneer of compact bone, and the bone's filled in with spongy bone. That actually makes bone stronger than it would be if it were all just solid compact bone. So, because of the strutting that actually occurs. Right. And so what we're going to see is that compact bone is made of a repeated pattern that we call an osteon. And there's very little space between osteons. And spongy bone is not made of that repeated pattern called osteons, which is why it has a lot of space. And then we're going to pick this up on Tuesday. So have a good weekend. So what do you want to do this weekend?